Today's webinar is about analysis models for estimating impacts and assessing baseline equivalence. We will discuss specific analysis models and walk you through the examples and a set of example data sets and programs for use with SAS, STATA, SPS, and R. The materials were created by Chris Price and Ann Wolf, and the webinar will be presented by me, Chris Price. The objectives of today's webinar are to provide guidance and orient you to technical assistance materials that are intended to help you specify and implement impact and baseline equivalence models that match your evaluation design. The objectives include helping you understand the importance of connecting the impact model and baseline equivalence approach, and learning how to implement the models and approaches using SAS, STATA, SPS, or R. The documents, data sets, and programs are all included in a WinZip file that can be downloaded from the link shown here. I would also like to note that this webinar and TA resources that we're discussing were prepared with an expectation that many or most of the education evaluations that utilize these designs may be reviewed by the What Works Clearinghouse, or the WWC. And we hope that the materials that we have produced will help evaluators plan, conduct, and report results from rigorous impact evaluations of the sort that can meet WWC standards with or without reservations. For today's presentation, I will be moving through each of the following topics. First, I will discuss aspects of the study design that should be reflected in the analysis models. The model should reflect the assignment strategies that were used. That is, whether individuals or clusters were assigned to treatment and control conditions, whether the assignment was within blocks or strata, and how the sample of study units was selected. That is, was it a convenience sample or was it selected from a defined population, and whether the inferences about the impacts are intended to generalize to that population. These aspects of the study design may be applied to either randomized control trials, which I'll refer to as RCTs, or quasi-experimental designs, or QEDs. So the models for RCTs and QEDs can have the same structure if they are similar on these design elements. I will introduce TA resources on analysis models that we have developed, including 2 guides, and example SAS, STATA, SPS, and R programs and data sets that you can use to fit the models we discuss to the example data. And I will be specifying and implementing, and then I will be specifying and implementing the models that match the design. As I walk through each of these models, I will talk about how to interpret the Greek model terms and how SAS, STATA, SPS, and R syntax corresponds to those Greek models. I will talk about using a modified form of the impact model to assess baseline equivalence of the treatment and control groups. And I will talk about formulas and code for standardizing the baseline treatment control differences. The models for estimating impacts and assessing baseline equivalence should reflect the study design. When choosing an analysis model, the model should reflect these aspects of the study design. The level of assignment refers to whether individuals, for example, students or clusters, examples include schools, teachers, or classes, are assigned to the treatment or comparison groups. In cluster assignment designs, clusters are assigned to treatment and control conditions, and the individuals within the clusters inherit the cluster status. That is, students in the treatment schools are treatment students. Students in the comparison schools are comparison students. Blocking refers to separating the sample into groups or maybe pairs, which we call blocks, and then assigning individuals or clusters to treatment and control conditions within each block. This approach is used to guarantee that within the blocking groups, some units are assigned to treatment and others to control. For example, in an RCT, if students were randomly assigned to treatment and control conditions within schools, the schools would be the blocks. Similarly, in a QED, control students were matched to treatment students within grades, within schools, then the grades within schools would be the matching blocks. Regarding generalizability, consider a study where you took a random sample of schools from all the public schools in a state. And within your randomly selected sample of schools, you randomly assign students to treatment and control conditions. In this example, if you want your inferences about treatment impacts to generalize to all schools in the state, then you should use an analysis model that includes random treatment effect terms. Okay, why does accounting for clustering assignment matter? Why is that one of our important elements? It's because failure to do so will usually result in standard error estimates that are too small. If the standard errors are too small, then the p-value from the impact estimate will be too small, and you may conclude that there was a significant impact when you really should not have reached that conclusion. The guidance documents and example data sets and programs use multi-level models to account for the correlation of individuals within clusters. Why does accounting for blocking matter? If individuals or clusters are assigned to treatment and control conditions within blocks, and the ratios of treatment to controls varies among the blocks, and the outcome means vary among the blocks, then failure to account for the blocks in the analysis could lead to really badly biased estimates of the impacts or the baseline treatment control differences. In RCTs with assignment within blocks, the treatment control ratio varies among blocks and the analysis fails to account for the blocks, then the study will fail to meet WWC evidence standards without reservations. In the coming slides, I'll use a small toy example data set with varying treatment control ratios among blocks and varying means among blocks to demonstrate how accounting for the blocks produces unbiased estimates of treatment control differences. But ignoring the blocks produces a badly biased estimate. In my example, I use baseline pretest data to demonstrate how ignoring the blocks can give the impression of a large baseline treatment control difference even where the groups are actually very well balanced. The same problem can occur with post-test data, but I'm demonstrating it with the pretest. In this picture, the open diamonds represent comparison group individuals, and the open circles represent treatment group individuals. The means of the individuals within a block are indicated with the horizontal lines. The individuals were assigned within these 4 blocks shown. These blocks could have been different schools or could have been 4 grades within a school. So the idea here is that this treatment and control students are matched or assigned within each of these 4, say, schools. Within each of these assignment blocks, the treatments and controls have the same baseline mean. The TC difference at baseline within each block is 0. These groups are very well matched. There are more controls than treatments in blocks 3 and 4, and the means in these blocks are very high, as you can see in this diagram. But there are more treatments than controls in block 1, and these have a very low baseline mean. If we use an analysis model that calculates the treatment control differences within each block, the difference is 0 in each block, and the averages of those differences will be the average of zeros. So the analysis would tell us that we have very closely matched groups, perfect match. These are the exact same data as were shown in the previous slide, but here we're ignoring the blocks. When the blocks are ignored, it looks like the controls had much higher scores than the treatments. It looks like the groups were way out of balance at baseline. But we know the balance was perfect within the blocks. If we use models that compute the treatment control differences within blocks, then the average within blocks, and then average the within block differences across the blocks, we're not going to have this problem of it looking like the groups are really out of balance when in fact they are very well balanced. Okay, how can model choice affect the generalizability of results? If your study units were drawn as a random sample from a defined population and you want the impact results to generalize to the full population, then the impact model must account for the fact that a different random draw from that population would have resulted in a different sample of study units. That is, the impact model must account for the sampling of variability that arises from selecting a sample at random from the population. Models with random treatment effect terms incorporate that sampling variability into the estimate of the standard error of the treatment effect. This will make the standard error larger relative to a model without random treatment effect terms, but will accurately account for the fact that each different sample could potentially be, each different sample could potentially have been drawn from the population will result in a different estimate of the treatment impact. The analysis models that we're discussing are used to so far are used to estimate the impact of the intervention, to compare outcome measures for the treatment and comparison groups. However, a model can also be used to assess baseline equivalence, that is, to compare the treatment and control groups on pre-intervention measures. We recommend using the same model structure for both the impact models and the baseline models. The example programs and data sets demonstrate how to do this. Before I discuss the models, I want to introduce the available TA resources. These include the guidance documents and the example data sets and programs. The reason I'm introducing these now is that when I go through the models that are in the guides later, I want you to be able to think about how you can use these example data sets and programs to fit the models to the example data using whichever of the 4 software packages you like best. When I discuss several model options for a single design type, I want you to think about how you can try the different model options with the example data and gain hands-on experience with how the models behave and what kinds of results they produce. The Analysis Models Toolkit includes 2 guidance documents. One focuses on specifying statistical models for estimating the impacts of the intervention, and the second is on assessing baseline equivalence of treatment and control groups in the impact evaluations. These 2 documents are organized similarly and are intended to be used in tandem. The toolkit also includes a set of example data sets and example programs in SAS, Stata, R, and SPSS that correspond to the designs and models described in the guidance documents. It's my hope that the evaluators will use the example data sets and programs to make a firm connection between the models specified in Greek notation and how those models translate to fitting models with real data and real software. I hope that when evaluators are writing their design plans, that they use the example specifications in Greek models that we've produced in these documents, perhaps editing, making some minor edits to fit their specific plans. The documents, data sets, and programs are all included in a WinZip file that can be downloaded from the link shown here. Here's what the 2 guidance documents look like, one for impact models, one for assessing baseline equivalence. When you open the zip file, I want to make sure that you see the subdirectory structure that's shown here. Click the View tab, then choose Show, then choose Single Folder, and it should look like this. Also, if you unzip the zip file to your local drive, I strongly encourage you to keep the subdirectory structure as shown here, with separate directories for the R, SAS, SPS, and Stata programs and files. In the example data sets and programs subdirectory within the zip file, there are directories for R data, R programs, SAS data, SAS programs, SPSS data and programs, and Stata data and programs. The right-hand panel of this slide shows the contents of the program subdirectory of the SAS subdirectory. The impact programs are numbered 1, 2, 3, and 4 to correspond to the sections of the guidance documents. Program 1 has SAS code for an impact model for a design with individual assignment and no blocking. Program 2 has code for several possible models that correspond to a design with individual assignment within blocks. Program 3 has code to fit a model for a design with cluster assignment and no blocking. And Program 4 has code to fit several possible models for designs with cluster assignment and assignment within blocks. Each of these programs reads in an example data set, fits the models to the data, and outputs results. In each program, I have also included code to convert impact estimates into standardized effect sizes, and code for outputting the key elements of the impact results that we recommend that you would include in your report. For additional guidance on what to include in your report, see our guidance document by Wolf, Goodson, Price in 2017 called Reporting Study Findings to Support Evidence Reviews. The programs to assess baseline equivalence within these subdirectories have names with A underscore or B underscore prefixes. Those with the A underscore prefix and a cont suffix on their names are for use on baseline measures that are measured on a continuous scale. For example, to check the baseline equivalence of a baseline achievement measure. Those with a B underscore prefix and a binary suffix on their names are for use on baseline variables that are measured on a binary scale. For example, checking the baseline equivalence of Pell Grant eligibility. Baseline programs 1A and 1B correspond to the same design as the impact program 1. Baseline programs 2A and 2B correspond to the same design and impact as the impact program for model number 2, and so on. The programs have the same names for all 4 packages, except that the extensions are different for each packages. All of the programs can be opened with any old text editor. The text editor I use is Notepad++, but the one that just comes with Windows will work fine also. The SAS programs have .SAS extensions. The R programs have .R extensions. The SPSS programs have .text extensions. And the STATA programs have .do extensions. In each of the programs, I have code for doing the analyses described in the guidance document. I've also cut and pasted some of the output from running the programs into the programs. The output's commented out so that it won't interfere with your running of the programs, but it's there so that you can compare code and output between the 4 statistical packages by looking at these commented pieces of output within each. Now I'm going to orient you to the guidance documents and programs for the most straightforward design, that is, individual assignment with no blocking. In the documents and programs, I call this Model 1. Model 1 is straightforward and is probably already familiar to most evaluators, but it will serve as a good place to get oriented about the example data sets and programs. Model 1 is a linear regression model and is appropriate for designs with assignment of individuals without blocking. As an example, consider a study conducted in a single university. In this study, all incoming freshmen in the fall of 2017 needing developmental math are randomly assigned to treatment or control conditions. The treatment students get a new developmental math course, and the control students get the business as usual developmental math course. A math achievement outcome is measured at the end of each semester. Model 1 is an appropriate model to use to estimate impacts for this design. On the left-hand side of the model, the dependent variable is the math achievement outcome for student I. Note that the outcome yi in the example data set are named ypost for y measured at post-test. On the right-hand side of this model, we have a treatment indicator, ti. It is a dummy variable coded as 1 if the student was assigned to the treatment condition and 0 if assigned to the control condition. Note that the treatment indicator, TI, in the example data sets are named treat. On the right-hand side, this model has covariates. The Y star I term represents a pretest of the outcome variable, and the X's after the summation sign represent additional covariates representing demographic characteristics of the student. Why does this model have covariates? The design is a QED, that is, students are non-randomly assigned to conditions, then the covariates can control for confounding. For example, if lower achieving students were more likely to be assigned to treatment, then the treatment effect would be confounded with baseline achievement. Controlling for baseline achievement can remove some or all of that confound. Additionally, for QEDs, the WWC review protocols specify that to satisfy evidence standards, that there are conditions when the impact model must include one or more specific baseline measures as covariates. The most common is when the magnitude of the treatment control difference on a pretest measure is less than 0.25 standard deviation units, but greater than 0.05 standard deviation units. Under those conditions, most of the protocols say that you have to include that pretest as a covariate. For RCTs with low attrition, the WWC would not require the use of covariates in this model, so those terms could be omitted. But including them often boosts the study's power to detect effects. So even for RCTs with low attrition, covariates are often included in the model. Note that the baseline pretest of the outcome, Y star, in the example data set is named Y pre for Y measured at pretest. The example data sets include 3 additional covariate X's. X1 is a binary measure coded as 1 equal yes, 0 equal no, for example, Pell Grant eligible. X2 is a continuous measure. For example, it could be age ranging from 17 to 21 years. And the third variable is called racecat. It's a categorical measure with 3 categories coded 1, 2, or 3. The SAS procedure proc-GLM can be used for fitting Model 1 to the example data. There is no natural ordering of the 3 categories of racecat, so we don't want the racecat variable to be used as a linear predictor in this model. Instead, we want our models to include 2 dummy variables to represent the 3 groups. Putting racecat in the class statement tells SAS to create 2 dummy variables to represent the 3 levels of racecat. The default for SAS and for SPSS is to make the last category of race, in this example, racecat equal 3, the omitted category. Note that even though the model has 2 dummies to represent the 3 categories of racecat, SAS shows 3 dummies in the output, but the last dummy has an estimate equal to 0.000 and missing values for the standard error, t-value, and p-value. That's its way of telling you that the racecat 3 category is the omitted category. It also puts B's next to all of the dummy variables when it does this. Don't let the B's bother you. They're not telling you that something is wrong, and they're always going to be there when you use the class statement as a way of making dummy variables. In R, we can use the LM function to fit Model 1 to the data. Here we tell R to treat racecat as a factor. This creates 2 dummy variables to represent the 3 levels of racecat. The default for R and for stata is to make the first category the omitted category. Remember in SAS and SPSS, the default was to make the last category the omitted category. To make it easier to compare output across the packages, in the example programs show how to tell R and stata to make the last category the omitted group. so that I've done this so that the output from all 4 packages will match. Note that the coefficient for the treatment indicator, treat, is the same regardless of whether racecat1 or racecat3 is the omitted category. The reason I show how to change the omitted category is that I thought it might be confusing if the output from the 4 packages didn't really match one another. In the baseline equivalence guidance document, we explain how to calculate the baseline treatment control difference using a modified form of the impact model. Here's impact model 1. Move the pretest from the impact model to the right-hand side to make it the dependent variable in the baseline equivalence model. Omit the other covariates in the model. Note that I renamed yi as base var I because this baseline variable could be a pretest or some other baseline characteristic. It could also be a continuous variable or it could be binary. In the example programs, in the example programs that have a prefixes and const suffixes in their names, the base variable is a continuous variable named ypre. In the example programs with b prefixes and binary suffixes in their names, the baseline variable is a binary variable called x1. When a baseline model is fit to the baseline data, the estimate beta naught hat is the baseline control group mean. The estimate beta hat 1 is the baseline treatment control difference. This is the thing we're trying to estimate here. And beta naught hat plus beta 1 hat is the baseline treatment control group mean. The base var I is binary, then beta naught hat is the proportion yes in the control group, and 100 times beta naught hat is the percent yes in the control group. And beta naught hat plus beta 1 is the proportion yes in the treatment group, and 100 times that is the percent yes in the treatment group. Later, I will show how the WWC standardizes baseline treatment control differences as part of the review process. The models get a lot more interesting and complicated when individuals are assigned to treatment and control conditions within randomization blocks or within matching blocks. In this section, I discuss 3 potential models for this design and describe how to estimate the baseline treatment control difference on the pretest using a modified form of the impact model. And I describe how to standardize that baseline treatment control difference. The guidance document on impact models shows 3 models that can be appropriate for estimating impacts for designs where individuals are assigned to treatment and control conditions within blocks. The first produces a single estimate of the treatment effect, averaged across the blocks. The second produces a separate impact estimate for each block. If you use this model and you want to have an overall impact estimate, you need to calculate the mean of the separate estimates from each block. The third model is useful if blocks were randomly sampled from a defined population and you want the inferences to generalize to that population. As an example of individual assignment within blocks, consider a study where within each of 5 universities, 2 cohorts of incoming freshmen needing developmental math are randomly assigned to treatment or control conditions. Math achievement outcomes are measured at the end of the semester for each cohort. In University 1 and Semester 1, students were randomly assigned to treatment and control. University 1, Semester 1 is an assignment block. In University 1 and Semester 2, a different set of students was randomly assigned. That is another assignment block. In University 2, Semester 1, that's yet another assignment block. All told, this study has 10 assignment blocks because assignment occurred within 2 cohorts within each of 5 universities. Here are a few important notes about the example data set for individual assignment with blocking. There are 10 blocks. Students were assigned to treatment control conditions within blocks. Within each block, treatment and control conditions have similar pretest values at baseline, so they're well matched to baseline within blocks. Between blocks, the means of Y pre vary considerably, and the ratio of treatment to control students varies across the blocks. Model 2.1 produces a single estimate of the average treatment effect. This model implicitly calculates a treatment control difference within each block and then calculates a weighted average of the differences across the blocks to produce an overall average treatment control difference, or an overall impact estimate. This model is similar to Model 1, but this one includes dummies for the blocks, or indicator variables for the blocks. The treatment estimate beta hat 1 is a precision-weighted mean of the treatment control differences within each block. Precision weighting means that the blocks with more precise estimates get more weight in calculating this overall average weighted treatment effect. Usually, treatment effects from blocks with larger sample sizes are more precisely estimated. Remember, because there was assignment within blocks, you can calculate a treatment control difference within each block, and then this model averages those treatment control differences across the blocks. Model 2.2 produces a separate estimate of the treatment effect for each block. It doesn't aggregate them. If you use this model, you need to calculate the mean of the separate estimates if you want an overall treatment effect estimate. This model has treatment by block interaction terms. It produces a separate treatment estimate for each block. The example SAS, Data, R, and SPSS programs show how to calculate an overall average effect from this model that is weighted by the number of students in each block. Model 2.3 is usually used in designs where the blocks were randomly sampled from a defined population, and you want the inferences about the impacts to generalize to that population. It is a two-level hierarchical linear model in which students, level 1, are nested within blocks at level 2, and the treatment effect is estimated at the student level. This model has random intercept terms for blocks and has terms for random treatment effects. The example SAS, Stata, R, and SPSS programs show you how to specify the random effect structure shown here. In this slide, we show how to specify a model for estimating the baseline treatment control difference that takes into account the design features in the same way that the impact model accounted for the design features. To do this, we specify a baseline model that is a modified form of the impact model. To specify the baseline model, we move the pretest from the left-hand side of the impact model to make it the dependent variable in the baseline model. We omit other covariates from the baseline model, but keep the treatment indicator and the block dummies. The coefficient from the baseline model, beta hat 1, is the design-adjusted baseline treatment control difference. This model does not ignore the blocks. Remember from the earlier slides that showed the potential peril of ignoring blocks in the baseline equivalence assessment. Now we're going to talk about how to standardize the baseline treatment control difference. The WWC assesses the size of standardized baseline treatment control differences. For continuously scaled variables, they use Hedge's G to standardize. For binary variables, they use Cox's index to standardize. The Hedge's G formula shown here is what the WWC uses to standardize the baseline treatment control difference for baseline variables that are measured on a continuous scales. For QEDs or RCTs with high attrition, the study has the potential to meet WWC evidence standards with reservations if the value of the Hedge's G is less than 0.25 standard deviation units for the relevant baseline variable, and if the impact model adjusts for the baseline variable. For example, it's used as a covariate. It can also pass with reservations if Hedge's G is less than 0.05 standard deviation units, regardless of whether the pretest is controlled for in the impact model. In order to ensure that y bar t minus y bar c in the numerator of this formula matches the baseline difference from the baseline model that accounted for the randomization or matching blocks, you should report the design-adjusted treatment group mean, which is calculated as y bar c plus beta hat 1, where beta hat 1 was the design-adjusted treatment control difference from the baseline model that accounted for the block design. That was the estimate from the model we just went over a minute ago. Y bar c is just a plain old mean in the control group. Note that you can, if you report the unadjusted treatment group mean, the WWC will use that and plug that into this formula, but you would be, both you and they would be ignoring the block design. And remember the perils of, potential perils at least, of ignoring the blocks. The example SAS, STATA, SPS, and R programs show how to do this standardization. In the example data sets and programs named Prog 2A with blocking, baseline equivalence underscore continuous, the standardized baseline differences are 0.053 standard deviation units. These are from the model that accounted for blocking. In the models that ignore blocks, the baseline difference is 0.30 standard deviation units. If this is what you reported, the QED would not meet WWC evidence standards because it's bigger than their cutoff of 0.25 standard deviation units. For binary measures coded as 0 or 1, for example, passed a course, failed a course, the WWC will use Cox's index to standardize the treatment control difference. PC in this formula is the unadjusted control group mean, for which a binary variable, for a binary variable is the proportion yes in the control group. When you're using this formula, use the design-adjusted treatment group mean for PT, where the design-adjusted treatment group mean is calculated as y bar c plus beta hat 1. Y bar c is the unadjusted control group mean. Beta hat 1 is the treatment control difference we estimated from the model that accounted for the block design. It may be okay, again, to just report unadjusted treatment group means, but again, if you did this, you and the WWC would be ignoring the block design, and we have to be aware of the perils of ignoring the blocks in block designs. Example SAS, STATA, SPSS, and R programs show how to do this standardization with example data. Okay, now we're going to talk about designs with cluster assignment, no blocking. In this section, I'll describe what is meant by cluster assignment. Then I will describe an example scenario of cluster assignment without blocking. I will reiterate the reason why multi-level models should be used for cluster designs. Then I will explain the components of the multi-level model. I'll start with the most basic multi-level model and explain what the terms in the models mean in words and graphically. And I will explain a slightly more complex models that include terms for a treatment indicator and covariates. These explanations are intended to help you understand how a multi-level model accounts for the clustering of individuals within the clusters, or the correlation of individuals within clusters. I will then show how to adapt a multi-level impact model to estimate a baseline treatment control difference on a pretest variable, and will point you to example programs that fit the impact and baseline equivalence models and standardize the results. In cluster assignment designs, clusters are assigned to treatment and control conditions. Examples of clusters include schools, classes, course sections, or instructors. The individuals within those clusters inherit the cluster's status. So students in treatment clusters are treatment students. Students in control clusters are control students. For an example, consider a design where middle schools are assigned to conditions. 103 treatment schools receive a math intervention. 50 comparison schools receive a business-as-usual math instruction. All sixth graders in the treatment and control schools will be given an end-of-year assessment. Pretests will come from math assessments given at the end of their fifth grade year, the prior year. This example data set has accompanying SAS, Data R, and SPSS programs for impacts and baseline equivalence in the zip file. In cluster assignment designs, as we've said, the analysis needs to account for the correlation of individuals within clusters. Failure to do so will usually result in standard error estimates that are too small. The guidance documents and example data sets and programs use multi-level models to account for the correlation of individuals within clusters. Here I show the most basic kind of multi-level model. It's an unconditional two-level model with students, level 1, nested in schools, level 2. Yij is the outcome for the ith student in the j school. Beta naught j is the intercept for the school, for the j school. Epsilon ij is the deviation of student ij's score from his or her school mean. At level 2, gamma 0, 0 is the grand mean of the outcome. Mu naught j is the random intercept term. It's the deviation of school's j's mean from the grand mean. The ICC, or interclass correlation, is a measure of the correlation of the individuals within the clusters, or within the schools. The numerator is the between cluster variance, and the denominator is the sum of the within cluster and between cluster variance. We're going to demonstrate all of these terms graphically in the slides that follow. This example shows the same model from the previous slide. It has a very large interclass correlation to make the correlation of students within schools look very obvious. So just looking at this, you can see that students are clustered very tightly around their school means. So the term gamma 0, 0 is the grand mean, shown with this dotted line across the overall average of all the schools. Mu naught j is the random intercept term. It's the deviation of school j's mean from the grand mean. Epsilon ij is the deviation of student ij's score from the school mean. These deviations of individuals around their school means are assumed to be independent, conditional on having terms for the school means in the model. So this is the way that the model accounts for the correlation of individuals within schools by having terms for school means and the deviations of individuals from their school means at the student level. You can see in this example with a very high interclass correlation how similar the students are within the schools. In this, the ICC in this slide at 0.10 is actually more typical of what you see in education interventions, but you can still see the correlation of individuals within the schools. This is the most basic two-level impact model. It adds a treatment indicator to the model. The treatment indicator is a level 2 variable because assignment is at the school level and the value of the treatment indicator is constant across all individuals within a school. So within a school, all students are either all treatment or all control. Here I show graphically what each of the terms in the impact model are. We add covariates to the model, it looks like this. Student level covariates, vary within schools. So things like a student's pre-tests are different among different students within a school. School level or level 2 covariates are constant within schools. So these, like the school average percent free reduced price lunch, is all students in the school have the same value on that. It's a school average measure. This model is shown in the guidance document with example data sets and programs. The baseline equivalence model can be adapted from the impact model by moving the pretest from the left-hand side of the equation, dropping the covariates, and keeping the random intercept terms. The coefficient for gamma hat 00 is the design-adjusted baseline treatment control difference. You can standardize this as described previously. The example programs include the code to standardize treatment control differences using Hedge's G and Cox's index. You can try this with the example programs. Program 3 is the impact model, 3A is the baseline model for a continuous baseline variable, 3B is the baseline model for a binary variable. In the interest of time, I'm not going to go through the models for all the additional designs that are described in the TA guidance materials. The concepts of accounting for clustering and blocking were discussed earlier in this presentation, and those concepts generalize to the cluster assignment within blocks design and the stratification many-to-many using propensity scores design. Please use the guidance documents and the example programs and data sets to learn more about specifying and fitting impact and baseline equivalence models for these designs. Example data, SAS, STATA, R, SPSS programs for this design for impacts and baseline equivalence are all included in the zip file. I've presented a lot of material in this presentation. We don't really expect you to necessarily absorb all of it just as I blasted through it, but we hope that you're now well oriented to the materials and that you can use this set of materials to help you specify and implement impact and baseline equivalence models that correspond to your study design, and to convert the treatment control differences into standardized metrics using Hedge's G or the Cox index so that you can assess baseline equivalence and can report results. Thank you for your attention and good luck with your analyses.